Okay, cool. Okay, it's working. Okay, thank you, Abel and Charlie for coming. I apologize that I will not be there Monday. Been traveling too much this semester. But anyway, I think Zoom is a new way to teach, and it works out actually. So anyway, so last class we talked about the Internet Control Message Protocol and what problems, security issues it has. Some of the attacks utilizing or exploiting ICMP, a lot of that useful anymore, but still the philosophy, the attack philosophy behaving are same or similar to the attacks we apply to other layers. So today we were keep looking at the IP layer and what attacks are there. So IP protocol was designed in the late 70s or 80s, and it was part of the DARPA Internet project, and it was a very small network, right? So all the hosts, they were known, the users, they were known, so there was no security issues. So it's like a lot of systems, when they were designed, they didn't have this security in design in mind. They design the system first, they make it work first, then later they find out there are many issues. So the security flaws in IP, if we look back, we will say there is no data integrity, there is no confidentiality, there is no encryption to protect the payload. The payload in this case will be upper layer protocols like TCP, IP, or just other layers of application data. Of course, this is a problem for other network protocols at that time as well. There is no integrity, there is no confidentiality. And also the source can be spoofed. So not only the data can be modified, can be tampered, but also the header of the IP. There is no authentication, there is no integrity or authenticity on those headers. Also, the IP fragmentation mechanism can also be exploited. That's some software implementation issues, which we will talk later. So, what is a source spoofing? So this is basically the same as the MAC address spoofing. The IP addresses, they are just logical addresses. They are filled in by the originating host. So the host can claim any IP address he wants to claim. For example, we have a network, and the two networks, they are collected through the internet. Then there is a say has a IP address 2.1.11. Then we have several other hosts in another network. So if a host A wants to claim to be a host S, it's just as simple as changing its own IP. That's it. Not necessarily really changing its IP. It can only just change all the IP diagrams it sends out, change the header to pretend to be somewhere else. So this actually was an issue many years ago. There was a suite of software called the R software. So one of the software is called the R logging. This is a software for Linux systems that allows users to log in on another host via a network, communicating through the TCP protocol using port 513. So this is kind of like a telnet or SSH right now. So it's a remote logging application. However, this application, the user can specify trusted hosts in a local file. Let's say Alice has a computer A and B, and Alice wants to, let's say A is Alice's workstation in company, and the host B is Alice's computer at home. If Alice add a trusted IP list into the workstation, as long as Alice use a computer with that IP address to log in, then there is no need to input any password. Basically, that host is trusted. So you can say this is an IP address based authentication, basically. But IP address can be spoofed. Anyone can claim whatever IP address they want to claim. So this is not really a secure protocol. And many other R utilities, R suite applications have the same issue. So we're not using those applications anymore, but they did exist in history. Now we use SSH or S-copy, secure copy instead. S-copy is based on SSH. And using those tools and also protocols, we do not allow host-based authentication. You cannot simply authenticate yourself using the IP address. You can use either a password or you can use the challenge response protocol we discussed before to do the authentication. The idea behind this is very simple. It's just a challenge response. Of course, there are a lot of details there, like I showed you guys in the FIDO protocol and other protocols. The basic idea, challenge response diagram, a lot of details to add new features there. In this case, let's say the simplified version is like Alice has public key, private key in host B, and host A has Alice's public key, but no one else has Alice's private key on host B. Even attacker, host C do not have that. Then we just do a challenge response. When Alice wants to log in the host A, the host A will send a random number to Alice. The Alice will encrypt that using private key. Then host A can verify that by decrypting the message using Alice's public key. Host C or any other malicious host on the network will not be able to log in host A because they do not have Alice's private key. Of course, the SSH protocol is more complicated, but the basic idea is just this challenge response diagram. Of course, or people will also say to defend against those kind of IP spoofing, we can use network gateways to block packets from outside the network. And if the source address is not in this network, we just block that. So this approach can prevent an outside attacker spoofing the address of an internal machine. Okay. Also, it can prevent an internal spoofer try to attack outside the world. However, this cannot prevent an inside host to spoof other hosts in the same network. That's because
நாளைக்கு இப்ப வைக்காத கை இப்போ காலையில பண்ணிட்டு குளிக்கலாம். தயவுசெய்து இப்ப நீ போட்டனா again you have to குளிச்சுப்பா. இப்ப கேவலமா நாறுது. இப்ப குளிப்பியா? இப்ப விட்டு இப்ப என்ன பண்ண?
I guess I need to mute you there.
Class.
Yeah. Okay, sorry about that. Okay, so then how do we defend against spoofing? Well, one way to do this is upper layer. Actually, they have some mechanisms can help defeat spoofing. Even though those mechanisms may not be directly designed for this purpose. For example, the TCP protocol, the transmission control protocol (TCP) uses sequence numbers in each TCP package, and that sequence number is negotiated with a remote machine, and to ensure that the arriving packets are part of an established collection, and we use the sequence number to reorder the packets. However, because of this feature, if someone wants to inject TCP packets, which is also an IP diagram, but if they do not know the correct sequence number, they will not be able to inject that. Okay, so even though the sequence number is not designed to defeat IP address spoofing, it will to some extent to make the IP spoofing not working. There are some other approaches that are designed to secure the IP layer. One of the protocol is called IPSec, the Internet Security Protocol Suite. This protocol suite has many different versions. I believe I remember all of the versions can well, some of the versions implies this. Anyway, so one of the version is called authentication header, and this authentication header is designed to verify the source of IP addresses. Basically, the IP header will be authenticated. There will be a crypto integrity authenticated code attached to the IP header. And also the IP fragmentation can also be exploited. This is a slightly different issue. Let's say we talked last class that all the network packets, the diagrams, the data units on the network, there is a maximum size. For example, Ethernet can only be 1500 bytes. Each Ethernet frame can only be that size. It cannot be bigger. It can be smaller, but cannot be bigger. However, the IP packet, which is at a higher level, can be larger than that. Okay, because the IP packet is larger than the Ethernet MTU, then the network card or the router, they have to break the packets into smaller packets. So the physical Ethernet will be able to deliver the message. And this approach is called the IP fragmentation. Each IP package, in this case, we call it IP fragment. So this not only happen at the IP layer, also happens in TCP layer as well. So let's say host A has a huge packet, which may be 100 bytes, 100 megabytes file they want to send to host B. Then host A eventually has to send this through a physical network to the router. And let's say if the physical network can only allow maximum 40 bytes of message, then the network adapter, the physical device, has to divide the big packet into smaller packets. Then the router may have a lot of different physical collection with another router, and that physical collection only takes 30 bytes for each packet. Then the router's physical network adapter has to further divide those packets. Then eventually, when the packets arrive at host B, host B will assemble those packets together and get what originally host A sent to B. Here is one example. Let's say we want to send an IP packet, which is 110 bytes. Let's say the physical network can only take 40 bytes. Then the original diagram, which is one IP header and 90 bytes of payload here, will be divided into 5 diagrams. And each diagram will be a new IP packet. They all have their own IP header, and they have the payload divided into all 5 diagrams of them. To do that, obviously, the IP protocols, they have some fields to help to make this happen. There is the identification field. There is also the fragment offset field. The first packet, the fragment offset field will be 0. The last packet here, the fragment offset will be something like 100. Okay. So a possible attack here is something called the IP fragment overlap. So basically, someone in the network, they can create malicious fragments. They can create fake IP packets, but those IP packets will follow some of the rule of the other legitimate IP packets which is already in the network. Then they can overlap those packets by manipulate the offset address. So to make the offset overlapping, to make some of the packets overlap with each other. And some of the TCP IP stack implementations will trigger a software issue when this happens. And because of this, the system will crash and it will be a denial of service attack to some of the TCP IP implementations. Okay, like I said that IP is not secure, have all those issues. And the most serious issue is still that the data, even the header, was not authenticated. So one solution to this problem is the IPSec protocol we just discussed. Then we will look at what is IPSec and how it works. So IPSec can protect the IP layer diagram and also upper layer protocols like TCP or UDP, depends on which IPSec mode you choose to use. And the IPSec is applicable to use over local network. It's also usable for public and private or bigger network or even internet. It has many different modes. It has host to host mode to get a host to host secure IP level communication. It also have host to gateway mode and also gateway to gateway mode. So all of you have been using IPSec. You just don't know you are using it. So later I will show you more examples there that you can see. Actually, you have been, why I say all of you have been using IPSec. So the IPSec protocol, it's actually a very complicated protocol. So in this course, we will only talk about the high level idea. And the IPSec has the following main components. One is an authentication protocol called the authentication header or AH. Another one is a combined encryption and authentication protocol. So not only authentication, but also for encryption. So this is called the encapsulating security payload, ESP. To support those protocols, there are also key management and exchange protocols. The default one is called the Oakley protocol. So like we said, the AH and the ESP, there are two different protocols in IPSec. They can be used alone, and also you can use them combined. You can apply ESP first, and then you can apply AH again. So the ESP protocol doesn't really authenticate the new IP headers. Later you will say what this means. And the AH protocol authenticate the original IP headers. Let's skip the comparison part. We just want to look at the protocols. The IPSec modes, there are transport mode, which we can use to secure two end hosts. So everything in the network can be malicious, but end-to-end computers, they can use this transport mode to create a secure communication channel between them. Also, there is something called the tunnel mode. The tunnel mode can be a gateway to gateway, which like a router to router, or it can be host to gateway. So this is the most commonly used protocol, actually, the tunnel mode. So the reason I say that all of you have been using this is because all of you used the UB VPN. At least for my course, you need to access the my software security class server to finish the homework. And that server is sitting on UB campus, and you can only access that when you VPN into UB network. And VPN is actually based on this IPSec tunnel mode. Basically, your computer connects to the UB UB router. Then you have a host to gateway tunnel mode. Everything between your host, your computer, and the UB VPN server is encrypted. No one else were able to say that in the network. For example, you may have a roommate with you using the same home Wi-Fi network. When you VPN into UB's network, your roommate will not be able to sleeve what you are sending to the UB network. Okay, so like I said, VPN is what everyone has been using, and the VPN is not really a physical network, and it's a private network, and the tunnels are built between your host and UB's router, and the tunnels are encrypted, provide the confidentiality. I will skip this page because now everyone is familiar with VPN. Everyone has been using VPN. Okay, then now let's look at how this is really implemented at the header level. So how the IP headers are changed when you use IPSec, and how they are changed when you use transport mode, and how they are changed when you use tunnel mode. Let's say in this figure, we have the original IP diagram. The IP diagram looks like this. It has an IP header. Obviously, in this case, we don't care about the Ethernet header. We don't care about the data link name from. We only care about the IP layer and upper layers. So we have the IP layer header, we have the TCP header, and we have user data. The user data here could be HTTP request. It could be any other application level protocols. So if you are using IPSec transport mode, then we were basically use our original IP header. After the original IP header, we will add a new IPSec header. After that, it will be the original data. Of course, in this case, the original data could have been encrypted or something. Then for the tunnel mode, the structure is different. First of all, we create a new IP header, which is different from the old IP header. The old IP header, the original IP header, will be used as the inner IP header, and this one will not be changed. So before that, we will have IPSec headers. So imagine this turtle mode message you send from your computer to the UB VPN network, VPN server. Then the VPN will strip the outer IP header and strip the IPSec header and use the inner IP header to find my software security class server, right? So you originally, when your computer construct the IP package to my server, then you will have my server's IP address, your virtual IP address in that network. So give your host a feeling that you are actually in the UB network, you are on campus, but actually it's not. That is achieved by this outer IP header and IPSec header. So the IPSec module is used to manage security for individual collections to other modules. There are security policy database provides specifications of the security service to be applied to each packet. Security association database contains the security parameters, what encryption algorithms we can use, what mode we can use, initialization data, session keys, and a collection from one module to another is created through a security association that corresponds to an entry in that security association database. And a security association is a unidirectional collection that defines the type of security service and mechanisms used between two modules. So IPSec is like I said, it's very complicated protocol. You don't have to know all the details. For this class, you only need to understand the difference between terminal mode, the difference between transport mode, especially this slide is important. You need to understand why this works. So other parts I will also explain, but you are not required to. I'm not going to put this in the basically in the file. So security association, like I said, is an association between a sender and a receiver. It consists of a set of security-related parameters like sequential numbers, the encryption keys, and obviously they are not fixed. They are generated and customized for each traffic flow. And each security association is uniquely identified by three parameters. The first one is the security parameters index, SPI. Another one is IP address. And also the security protocol identifier indicates whether this association, those parameters are for an AH or for ESP. So more than one SA can be applied to a packet. Like I said, that's because you can apply multiple layers of IPSec to a packet. You can do a ESP first, then on top of that, you can do another AH. So let's skip those details. Let's look at one example. The IPSec policy may look like this. The policy is all traffic to this IP address must be used pre-hashed key authentication. The DH group, which is Diffie-Hellman group, is this with this. So they used a modified Diffie-Hellman algorithm to negotiate keys. And the hash algorithm, we're going to use HMAC SHA 128, and we're going to use 3DES for encryption. So those are basically the parameters we're going to use for this collection. Then in IPSec, we represent them in something like this. Then they will be stored in the database, and the users will exchange those information. This part let's just skip because it's related to the architecture of IPSec, and I feel you don't have to understand this part in this class actually. Okay, so actually we have a very short class today. 3 of you are here. Do you have any questions? Okay, if you don't have any other questions, thank you for coming. I will see you guys next Wednesday. Okay. Yes, I will update the slides soon. Cool. Thank you. Bye.